Okay, our second and last speaker of the afternoon is Matthew Wiersma, that will talk about new tensor product of sister algebra and characterization of rigidly symmetric sister algebra.
Thank you for the introduction. I'd also like to thank the organizers of this conference, as well as this workshop here, for inviting me to speak. So the work that I'm going to speak on is joint work with, Han-Hee Lee, who's at Seoul National University, and Ebrahim Soumeh, who's at the University of Saskatchewan. Saskatchewan's, I don't know, almost like the next town over from Winnipeg, so around 800 kilometers away or so. All right, so a little bit of motivation. So let's suppose we've got two C-star algebras A and B. When we take the algebraic tensor product of A and B, can be multiple different ways of turning this into a C-star algebra. So there's two canonical ones. We have the minimal tensor product of A and B, as well as the maximal tensor product of A and B. And true to their names, the minimal tensor product is going to be the completion with the smallest C-star norm, and the maximal tensor product is going to be the completion with respect to the largest C-star norm that you can place on the algebraic tensor product. And in general, these two do not need to be the same. And it's natural to ask, well, can you get anything else? And what any other C-star completions of the algebraic tensor product of A and B? Well, in 2016, Ozawa-Pisier published a paper that said, yes, you can, at least in some circumstances. So their paper was entitled that B of H tensor B of H admits a continuum of C-star norms. But what they actually prove is quite a bit more. So if you have two non-nuclear von Neumann algebras M and N, for example, bounded operators on separable Hilbert space, and the algebraic tensor product of M and N admits a continuum of C-star norms. And further, each of these norms arises from a prescribed family of injective bifunctors. Okay, so they actually construct bifunctors on the class of C-star algebras, which maps every pair of C-star algebras AB to a C-star completion of the algebraic tensor product AB, such that, well, as your parameter varies, you get a continuum of different ones. Now, these are not the first examples of intermediate or exotic C-star completions of the algebraic tensor product of two C-star algebras. So for example, if you've studied von Neumann algebras, you may have seen the binormal tensor product of them before, which is something very useful. So the binormal tensor product is denoted by so. I'm not going to define it for you. However, it is only defined when M and N are von Neumann algebras. You try to take one to be a C-star algebra that's not a von Neumann algebra, well, this isn't defined. So the binormal tensor product is not a bifunctor on the C-star algebras, which is basically what that line says there. Okay, so what I'm going to do today is begin by describing some new bifunctors that give us new C-star algebraic completions of A tensor B. Before I tell you about these, I want to tell you where the motivation comes from. The motivation comes from exotic group C-star algebras, or in other words, completions of group rings with respect to C-star norms that are intermediate to the reduced C-star norm and the full group C-star norm. In 2013, Brown and Guentner introduced the so-called LP C-star algebras, which I'm not going to define for you, but these really caught a lot of traction. A whole bunch of different mathematicians studied them. So here's a list there, not going to read it off, just showing you that it really did attract quite a bit of interest. And you might ask, is like, well, can we find some sort of C-star tensor product analog of this construction here? And if you just look at the definition of how these are defined, these functors here, it's not really clear how you would do so, because the definition of this really depends on the representation theory of G in some sense. However, in joint work with Ebrahim Soumeh, we found another description for many different groups. So we showed that the LP C-star algebras in Brown and Guentner are going to be precisely the same thing as the enveloping C-star algebra of some Banach star algebra, which I'm not going to tell you what it is. Okay, so they're going to correspond to the enveloping C-star algebra of some Banach star algebra for many locally compact groups, including Kunja-Stein groups. This includes all semi-simple elite groups with finite center. as well as many discrete groups such as the free group. So rather than trying to work precisely with this description here, well, we're instead going to work with some sort of analog of this enveloping C-star algebra that we have there. Okay, so I'm now going to move on to describing the construction. So for the time being, let's assume that we've got concrete C-star algebras. So that means C-star algebra A, which is going to be a C-star subalgebra of B of H. And then I want to make some comments on the opposite algebra of A. So of course, this is going to be a C-star algebra. And we're able to concretely represent it inside of bounded operators on H bar. So if little a is an element of our C-star algebra big A, I'll let A op denote the corresponding element in the opposite algebra. Well, if we just identify this with the Banach space algebra, with the Banach space adjoint of A belonging to B of H bar, well, this gives you a star representation, an injective star representation. So indeed, we do get this correspondence here. So for a concrete C-star algebra, when I write A op, I'm really just going to mean that this, you can identify this with this Banach space adjoint of A right there. Okay, so let's suppose that A and B are concrete C-star algebras, A represented on a Hilbert space H, B represented on a Hilbert space K. And we're going to take P a value between 1 and infinity. We're going to embed the algebraic tensor product of A and B inside of the completely bounded operators of the Schatten P-class operators from K bar to H. And the way that we do this, so we're going to call the representation pi sub p, is for an elementary tensor A tensor B, pi p of this elementary tensor applied to T is simply going to give us the operator A, T, B op. Okay, and then we get that pi p is going to give us a contractive representation of A tensor B. And when we take the image of the algebraic tensor product and take the closure inside of the completely bounded operators on the Schatten P-class operators here, what we get is going to be a Banach algebra. In fact, it's going to be a completely contracted Banach algebra. And we denote it by A tensor sub P, C of B. The reason that we're using a C there is to denote that we're working with concrete C-star algebras. Okay, so this gives us a Banach algebra. And in the cases when P is equal to 1, 2, or infinity, we're able to say a little bit about what this Banach algebra is. All right, so again, A and B are going to be concrete C-star algebras. When P is equal to 2, you get precisely the minimal tensor product of A and B. And in that case, you get that it's going to be, yeah, this occurs isometrically, but it's not going to happen completely isometrically in general. So I'll go back one slide, here we go. So we do get that our construction here is going to be a completely contractive Banach algebra, which is a Banach algebra with an operator space structure that behaves nicely with respect to multiplication. However, we're really just primarily interested in how it behaves as a Banach algebra. So we're generally just going to forget the operator space structure because essentially the operator space structure of B gets all messed up when you do this construction due to taking the B op there. However, when it's no harder to make comments on the operator space structure, we still will. Okay, so we get this identification with the minimal tensor product isometrically. When P is equal to 1 or infinity, we can identify our tensor product with a twisted Hogrup tensor product. I'll say a little bit about the Hograp tensor product in just a moment. So the infinity tensor product of A with B is going to be A Hograp tensor product with B op. And the one tensor product of A and B is going to be B op Hograp tensor product with A. So what is the Hograp tensor product? Well, the Hograp tensor product is not a C-star tensor product. it's a tensor product in the category of operator spaces. And I'm going to give you a definition that's equivalent to the original one. If you have that A and B, or rather X and Y are operator spaces, well, then we can embed them completely isometrically inside of C-star algebras A and B. And we'll define the Hogrup tensor product of X with Y to be the inclusion that we get of the algebraic tensor product of X and Y inside of the full free product of A with B. And what inclusion are we taking? Well, what we do is, for an algebraic tensor product of A and B, we embed this inside of the full free product by just sending the elementary tensor A tensor B to AB. Okay, it turns out that this construction here is independent of your choice of embeddings and is equivalent to the Hogrup tensor product. Hogrup tensor product has all sorts of nice properties. It's, of course, associative. It's both injective and projective, which is really nice. However, you do lose commutativity. So there's a reason why why instead of writing A tensor B op for both of these here, why I do have the B op written first, because it's not commutative. Okay, so we get these identifications here. All right, so our definition so far is defined for concrete C-star algebras. How do we define it for abstract C-star algebras? Well, the idea is to take an abstract C-star algebra and represent it on a Hilbert space. However, it's conceivable that you might get something different depending on what Hilbert space you choose. So the way we define it is really by taking a supremum over star representations of your two C-star algebras. So if you take X, an n by n matrix, or the algebraic tensor product of A and B, the norm of X, A tensor U sub P of B, so U here indicates universal construction, is simply going to be the supremum of pi tensor sigma applied to your matrix here, where pi and sigma range over all star representations of A and B. And here you're looking at the norm with respect to the concrete construction. And what we conjecture is that for a concrete C-star algebra, this universal construction that we've defined up above is actually just going to give you the same as what we had before. We know that this is going to be true when p is equal to 1, 2, or infinity. Why is this? Because when p is equal to 1, 2, or infinity, we're able to identify our tensor product with either the minimal tensor product of A and B or a twisted Hogrup tensor product. And both the minimal tensor product and Hogrup tensor product don't care about how you represent it, how you represent your C-star algebras. And further, well, I think I've stated this, we expect it to hold isometrically. We also expect it to hold completely isometrically. Now, the tensor products that we've defined, they produce Banach algebras, not C-star algebras at the moment yet. We'll work towards producing C-star algebras, but they have pretty nice properties. So first of all, they're commutative, and the commutativity holds isometrically. Second of all, they're injective. So if we have that A naught and B naught are C-star subalgebras of A and B, and the P tensor product of A naught with B naught, either universal either universal or concrete construction, embeds completely isometrically into the P tensor product of A with B. Thirdly, they're functorial with respect to completely contractive maps. So if we have completely contractive maps phi from A to A prime and C from B to B prime, then we have that phi tensor C extends to a completely contractive map from the P tensor product of A with B to the P tensor product of A prime with B prime. Question, yes? So let's see this one here. Yes, that will be a case. Let me think about that. Is that true?
It won't be true because one has B opposite that are at A opposite.
Oh, you're right. No, it won't be. I had to think about that though. Let's see. Yeah, it's because the,
It won't be, it's
yeah.
obviously true.
And in fact, I can say it's not true in some instances. I'll explain that a little bit later. But yeah, 1 and infinity, they're not going to be the same in general. But that's a good question. It's because, yeah, the Hogrup tensor product is not commutative.
Also, if you switch A and B on the left, then the new one has A opposite and B in some order. The old one had A and B opposite.
Yes, you're right about that also. Yes, yes. Okay, let's see, where were we? All right, so far what we've defined is a Banach algebra. However, it's not going to be a Banach star algebra. So the next step that we're going to do is sort of adapt our constructions to produce a Banach star algebra. Okay, so something that we can notice is that fx is an element of the algebraic tensor product with A and B, and a very straightforward calculation shows that x star, the norm with respect to the P tensor product of A with B, is going to produce precisely the same thing as the norm of x in the Q tensor product. Okay, so, and I should say here, P and Q are going to be Holder conjugate. So if we have P and Q are Holder conjugate, and A and B are, say, concrete C-star algebras, well then what we're going to define is going to be the PQ tensor product of A with B. The way this is defined is simply by taking the maximum of the P norm and the Q norm. Thanks to this here, this equation here, you get that it's going to be invariant under the involution on A tensor B, and so we get a Banach star algebra. And this construction, or this definition here that we did for concrete C-star algebras, you can also do it for universal C-star algebras, same definition at each of the matrix levels. And once again, you get a Banach star algebra. All right, and these Banach star algebras in some ways are much better behaved than the Banach algebra tensor product that we produced earlier. So we've got very nice inclusions between them. If A and B are C-star algebras, and 2 is less than or equal to P prime, less than or equal to P, less than or equal to infinity, and we take Q and Q prime to be the Holder conjugates of P and P prime, then we get that the identity map on A tensor B extends to an injective contraction of the PQ tensor product of A with B into the P prime Q prime tensor product of A with B. Okay, so we get inclusions between all of them, depending on what P is. And this gives us quite a lot. All right, and now what you've been waiting for, actually producing a C-star algebra tensor product. So once we have a Banach star algebra, what we can do is we can take the enveloping C-star algebra of it. And that's precisely what we're going to do. So for concrete C-star algebras, A and B, we set the tensor product A tensor C, so C is for concrete still, and C star PQ of B. We let this denote the enveloping C-star algebra of the PQ tensor product of A and B. And you do the same sort of definition for abstract C-star algebras, and we denote by a U at the top instead of a C. Okay, in the case when P and Q are equal to 2, you end up with precisely the minimal tensor product of A with B. And when P is equal to 1, Q is equal to infinity, or vice versa, it turns out that you end up with the maximal tensor product of A and B. And this is actually something quite subtle. If, say, you had the norm arising from the 1 tensor product or the infinity tensor product dominated the maximal C-star norm of A and B, then this would be automatic. However, this does not happen in general. So it turns out that Yemin Choi independently became interested in these twisted Hogrup tensor products several years before us. And something that he observed, phrased in slightly different language of twisted Hogrup tensor products, is that there actually exists C-star algebras A and B with the property that when you take the identity map on the algebraic tensor product of A and B, this does not extend to a bounded map from the one tensor product of A with B into the minimal C-star norm, or the infinity tensor product of A with B into the minimal C-star norm. So the one and the infinity tensor products do not even need to dominate the minimal C-star norm. However, when you take the maximum of the two of the norms, you get that it necessarily dominates the maximum. I find this a really compelling reason to study the symmetrized version of the tensor product. So something that's open that I'll mention is that we don't know whether our C-star tensor products here are functorial with respect to completely positive maps. So open problem, if A and A prime are C-star algebras, same with B and B prime, B from A to A prime, and C from B to B prime are completely positive maps, is it true that phi tensor C, does this extend to a completely positive map from this C-star tensor product of A with B, the PQ1, to the PQ C-star tensor product of A prime with B prime? Once again, we know that this is going to be true when P is equal to 1, 2, or infinity. Why is this? When P is equal to 1 or infinity, well, we end up with the maximal C-star norm. When P is equal to 2, we end up with the minimal C-star norm. And we know that both the maximal and minimal C-star tensor products are functorial with respect to completely positive maps. But we don't know whether this is true in general. Okay, so we've talked about a construction here. The natural question to ask is, does it actually produce anything interesting besides just the minimal or maximal tensor products? And yes, it does produce other things. And we're going to see this by taking a look at tensor products of reduced group C-star algebras. So first, a little bit of notation. Let's suppose that G1 and G2 are discrete groups. P is a value between 1 and infinity. We let SP of G1 cross G2, or the Shatton P-class functions on G1 cross G2. This is going to denote the set of all functions from G1 cross G2 into the complex numbers, such that the formal matrix U of ST, as S and T vary over G1 and G2 respectively, that this is going to be the matrix representation of some Shatton P-class operator with respect to an orthonormal basis. And in this case, if we happen to have that phi is a positive definite function on G1 cross G2, that belongs to this class of functions here, so the Shatton P-class functions on G1 cross G2, then we're able to conclude that phi necessarily extends to a state on the reduced tensor product of or the reduced C-star algebra of G1, PQ C-star tensor product, reduced C-star algebra of G2. And this is something that's quite useful. For certain groups, this, in some sense, almost characterizes what positive definite function extends to state on this C-star algebra. Okay, so we're going to consider free groups. So P is going to be a value greater than or equal to 2. And D1 and D2 are going to be two indices of free groups that are at least 2. Could be infinity. And phi is going to denote a positive definite function on free group with D1 generators cross free group with D2 generators. And we can characterize when this is going to extend to a state of the reduced group C-star algebra of the free group with D1 generators, tensor product against the reduced group's C-star algebra of the free group with D2 generators with respect to our C-star PQ tensor product. And so first of all, it extends with respect to our concrete construction. So the reduced group C-star algebra concretely embeds inside of bounded operators on L2 of the group. That's going to be equivalent to extending to a state on the universal construction here. which is equivalent to this third condition that states that phi in some sense almost belongs to the Schatten p-class functions of the first group across the second group. Okay, so it's saying that when you take the positive definite phi and multiply it by the function e to the negative alpha, word length of s plus word length of t, where s and t are your inputs there, the ordered pair, that this belongs to SP of FD1 cross FD2 for all values of alpha greater than 0. Okay, and perhaps I'll say a few words about the proof. So the implication 1 implies 2 is trivial. 2 implies 3. You're somehow using the fact that the free group has the rapid decay property. And then 3 implies 1. Well, what you do is if you take phi and multiply it by this function here, well, that's going to, if you have that, this right here is always going to be a state, or rather a state, or rather positive definite function that lies in here. And by the previous slide, it extends to a state on this tensor product here. And you simply take alpha to approach 0. Well, that approaches the positive definite function phi, so phi must extend to a state of this one also. Okay, and so the theorem, as I've stated it in this talk, is stated for free groups, but actually you're able to generalize this, and it holds for many discrete groups that have both the rapid decay property as well as the Hogwarts property. But to state it is a little bit technical, so I've decided to just state it for free groups. As a consequence of this characterization, we get that our C-star norms actually do produce something different from the minimal and the maximal tensor product norms. Okay, so in particular, if we have that 2 is less than or equal to p prime, less than p, less than or equal to infinity, and d is greater than or equal to 2, less than or equal to infinity, then the canonical quotient map from our PQ tensor product, or C star PQ tensor product, of the reduced group C star algebra of the free group against itself, into the P prime Q prime C star tensor product of, again, the reduced group C star algebra of the free group against itself, this is not going to be injective. In particular, each of our tensor products is going to be distinct as P varies between 2 and infinity. And once again, an analog of this result holds for many discrete groups with both the rapid decay property and the Hogwarts property. And so we now know that our constructions different from, or our constructions do actually produce a whole bunch of different tensor products. It's natural to ask, does it give us the same thing as the Ozawa-Pisier bifunctors? And we're able to say no, they're actually going to be something completely distinct. So each of the Ozawa-Pisier bifunctors, they have the special property of being injective. Ours are not going to be injective when p is not equal to 2. So by showing failure of injectivity, when p is not equal to 2, we get that there's no overlap, except for the minimal tensor product. And something that I want to mention is that the class of C-star algebras where we understand these well, in terms of knowing when they're going to be distinct from minimal and maximum and all that jazz, is quite different from where Ozawa and Pisier understand their bifunctors differ from the minimal or maximum. So the Ozawa-Pisier bifunctors, those are really well understood for von Neumann algebras, non-nuclear von Neumann algebras. You get a continuum of different C-star norms there. However, as far as I was able to tell from their paper, it's not known when you take the reduced group C-star algebra of the free group on 2 generators against itself, whether their tensor products ever differ from the minimal one. So I will mention that in their paper, they do produce also a continuum of C-star tensor products on, I guess, the reduced group C-star algebra of the free group against itself, but this was by using different techniques. They was using representation technique, representation theoretic techniques. Okay, whereas for us, we really understand things that, or tensor products that look like this very well. We're able to characterize what positive definite functions extend to a state on it. However, we do not know when we take bounded operators on separable Hilbert space whether our tensor product ever produces something different from the minimal tensor product when p is strictly between 1 and infinity. So that's an open problem. We don't know. We'd like to know that. And in my remaining time, I'd like to talk about an application that we found for these tensor products to symmetric Banach star algebras. So the topic of this workshop is symmetry and structure. I don't think that this is what the organizers were thinking of when they talked about symmetry, but it's the same name, right? We're close enough. So we say that a Banach star algebra is symmetric if when we take the spectrum, take a look at the spectrum of things of the form A star A, this is contained in the non-negative real numbers. Okay, and of course, we all know that C star algebras are symmetric. But this is something that's not immediately clear. When C star algebras were first introduced in an abstract form and given axioms, this condition of symmetry here was included as one of the axioms. It was later shown to be superfluous. And being symmetric as a Banach star algebra, it turns out it has lots of different applications and different characterizations. Just to give you some flavor, here are some equivalent characterizations for a star semi-simple Banach star algebra. So what does star semi-simple mean? It means that star representations separate points. Or equivalently, the canonical map of the Banach star algebra into its enveloping C star algebra is injective. Okay, so the following are equivalent. A is symmetric. Secondly, A is Hermitian, which says that the spectrum of self-adjoint elements is contained in the real numbers. Third, we have the spectral condition here, which is that if we take an element A of our algebra, then the spectrum of A in the original algebra, big A, united with 0, is going to coincide with the spectrum inside of the enveloping C star algebra, united with 0. And fourth is that the spectral radius inside of A and its enveloping C star algebra are one and the same for every element coming from big A. So you get a whole bunch of different interesting characterizations here. So I will mention that this theorem is not due to us. It's due to a whole bunch of different authors, or several different authors. It's quite a classical theorem. Okay, so before talking about, I guess, tensor products again, I'd like to talk a little bit about groups and again, part of what motivated this project here. So there's this old problem of Huliniski from 1963 that conjectures that if G is a locally compact group, whose group algebra L1 of G is symmetric, then the group must be amenable. And over the years, various progress was made on this. So in 1970, Jenkins showed that if the group algebra is symmetric and the group is discrete, then the group cannot contain a free subsemigroup on two generators. In particular, if your group contains a copy of the free group, it's not symmetric. Okay. In 1978, Huliniski verified this conjecture for connected groups. So completely solved in the case when G is connected. But in the case when G was discrete, it remained open, and there were several other contributions in the meantime, which I haven't mentioned here. In earlier work, Ebrahim Sameh and I solved this problem, and we showed that Huliniski's conjecture is true. In particular, if the group algebra L1 of G is symmetric, G is going to be amenable. Okay, and solving this, we introduced really a new technique. It wasn't really a variation on old techniques, it was sort of a brand new technique. And we were sort of looking for ways to apply this. In the meantime, I guess Ostad and Ortega, who are, I believe, both in the audience here, they proved a generalization of our theorem, and there's been lots of talks about groupoids in this workshop. Well, they proved that if L1 of G, or that if you take the L1 algebra of a twisted groupoid and it's symmetric, then the groupoid must have the weak containment property. So that's very nice. So they got that generalization. But we were more interested in some sort of generalization of this or application of the technique that we developed for C-star algebras. Okay, so of course we're not going to be talking about what C-star algebras are going to be symmetric because they all are. That's not an interesting question. But there's this other related notion of being rigidly symmetric. So if A is a Banach algebra, or Banach star algebra rather, we say that's rigidly symmetric if when we take the Banach space projective tensor product against any C-star algebra, what results is symmetric. And in terms of applications, quite often, rather than dealing with just a symmetric Banach star algebra, you'll actually want to be dealing with a rigidly symmetric Banach star algebra. Okay, so for example, this is a classical theorem of Kugler. You prove that if you take a type 1 C-star algebra, it is necessarily rigidly symmetric. And asked in the same year by Leptin and Pagunka is, do the notions of being rigidly symmetric and symmetric, do these ever differ? And this was repeated a couple times throughout the years, in particular by Pagunka in 1992, and it was asked by several other authors in the special case of group algebras, L1 of G. This by several other authors in subsequent years, in the special case of L1 of G, where G is a locally compact group. And in 2012, a paper appeared that stated that if you take any C-star algebra, then it's necessarily rigidly symmetric. Unfortunately, it contained an error, and actually, we've shown that C-star algebras are not necessarily rigidly symmetric. Proof in retrospect is not very hard. So I will mention that in terms of applications of rigidly symmetric, all these authors here were really primarily interested in the case of L1 of G, working on convolution bounded operators and this sort of thing. A lot of their techniques really tend to work when L1 of G is rigidly symmetric. So that's where they were most interested. But we've been able to cook up an example of C-star algebras, of a C-star algebra that's not rigidly symmetric. And it's not too hard. I can show you very quickly. If you take the Banach space projective tensor product of the reduced group C-star algebra, the free group, against itself, we can see that this contains a copy of little L1 of Ft. Okay, so if we take a function in little L1, well, we can just embed it diagonally inside of this Banach space projective tensor product here. This embedding here is isometric. So what we get is, well, L1 here embeds inside of this Banach star algebra. But it turns out that closed star subalgebras of symmetric Banach star algebras are themselves going to be symmetric. Guess what? Little L1 of G is not symmetric, so therefore this can't be either. Okay, so we now know that there do exist Banach star algebras that are going to be symmetric, but not rigidly symmetric. But we're able to say quite a bit more. We can actually characterize what C-star algebras are going to be rigidly symmetric. Turns out that the converse of Kugler's theorem is also true. So we have that a C-star algebra A is going to be rigidly symmetric precisely when it's type 1. Okay, and it's also equivalent to this third condition here that I will mention. Before that, I'm going to introduce a quick definition. So let's suppose we have a star subalgebra S of a Banach star algebra A. And here we're not assuming that S is closed. Okay, we say that S is quasi-symmetric inside of A if really the same sort of symmetry is the same definition of symmetry holds. So the spectrum of A star A is contained in the non-negative real numbers for all A coming from S. So here we're not asking for all A from A, we're asking for all A from S. So the equivalence of A being type 1 and rigidly symmetric is also equivalent to the algebraic tensor product of A and B being quasi-symmetric inside of this PQ tensor product of A and B. So this is our Banach star algebra tensor product. For some, or equivalently every, non-type 1 C-star algebra B, and some, equivalently every, value P not equal to 2. So all of a sudden we see our PQ tensor products popping up again. And I will mention that I do not know a way of proving the equivalence of 1 and 2 here without working with our PQ tensor products. So our proof, working with our constructions here, are absolutely essential. As a consequence, if we have that two C-star algebras A and B satisfy the property that their Banach space projective tensor product is symmetric, well, then we have that A and B, or A or B is going to be type 1, and conversely. So we get a complete characterization of when the Banach space projective tensor product of A and B is going to be symmetric, precisely when A or B is type 1. And one more interesting corollary that we found quite surprising is that there actually exists rigidly symmetric Banach star algebras whose enveloping C-star algebra is not rigidly symmetric. Somehow you'd think that, you start with some sort of Banach star algebra, taking the enveloping C-star algebra, well, that ought to make things more symmetric because C-star algebras are symmetric, right? But it turns out this is false. And it's not too hard to see this in light of, some theorems of, I guess, Leptin and Punguka and Thomas. So here's two facts that we're going to use. If G is a finitely generated group of polynomial growth, then little L1 of G is rigidly symmetric. And the second fact that we're going to use is that if we have a discrete group G, then its full group C-star algebra is going to be a type 1 C-star algebra precisely when G contains an abelian group of finite index. So taking a look at these two facts, we get a method of producing examples of rigidly symmetric Banach star algebras whose enveloping C-star algebras are not going to be rigidly symmetric. If we take G to be any finitely generated group of polynomial growth that does not contain a finite index abelian subgroup, for example, you can take a discrete Heisenberg group like so, well then, L1 of G is going to be rigidly symmetric, but the enveloping C-star algebra of L1 of G, which is the full group C-star algebra, is not type 1, and hence not rigidly symmetric. So we do get this here. And I'll end here. Thank you very much.